Everyone, welcome back to the binary tree machine learning course. This is, of course, week three. Sorry, this is week three, polynomial regression and model tuning. But first, let's do a quick recap of week two in case we forgot, because we just want to make sure that we have the basics down before starting up week three, which is an extension of what we did before. So, as we remember, there's something called a linear regression where we take a linear model and fit it to some data. There's a slope, y-intercept, and it's basically used to predict at some given value what is the y-axis, at some x value, what is the y expected value supposed to be. We said that there's something called residuals and that we need to square them and create the mean squared error loss function and create our least squares regression line. And then we also have to create a test train split where we split our data into two parts, which is training set and testing set, where we fit our model on training, and then on testing, we actually test it out. On test data, it tells us how good our model should do on new data. And we talked about regression versus multiple regression, where we add another variable to kind of explain what may be influencing the prediction. Now, we're here at week three. We need to talk about using x to predict y. Once again, it's the same thing. But here, we see it's not really following the same shape as before. Before, we just talked about lines, right? We said, okay, here's a line, it fits, but a line's not really going to fit here, right? So you can see in this sense, it's more of a curved shape. But what kind of shape would fit this? A line? No. A line really wouldn't fit it. If we try to line out, it gives us a pretty high mean squared error here. It gives us a 7.54 error because we see here at the lower and higher points it's okay, but in the middle points it really curves up past that. How can we do better? Well, that's where quadratic regression comes in. We added an x squared term to our model. So what that does is now it fits a quadratic equation, a parabola curve. If we've learned this, it fits this kind of curve to the data. And now we have three weights to the model. We have the y-intercept, we have the beta 1 value, which is our linear slope, and now beta 2, which tells us the quadratic slope. So it basically tells us for the quadratic term, what is the rate at which that changes. So we've added that curvature part to it. Will this have a lower or higher MSE than before? Well, it looks like it should have a lower MSE. It does, right? It's 2.81 because the fit is simply just better. The fit looks a lot better. Now, can we do better? Yes, of course we can do better. We can add in a bunch more terms, make it cubic, quadratic. We can make it polynomial by adding a lot of variable or adding a lot more terms and making it specific to fit this. So why don't we just do that? Of course we can. I mean, we can do this for any data, right? Why don't we just go ahead and make it that kind of fit? Because it looks like it fits perfectly. Well, it has an MSE of 0. It looks perfect. But this is kind of a trick question. Or trick in the sense, is this model good for predicting new data? Let's think about that. How can we predict which model does best on predicting new data? Well, we can use our test. So we had our train and now we're using our test. Looks like model A we knew wasn't good, but between models B and C, model B actually performed better than model C. But why is that? What is the reason that our seemingly amazing model didn't perform so well on the fit versus our decent model actually worked better? Well, the reason is overfitting versus underfitting versus well tuning. This is the whole concept of tuning our model to our data. If the model's too simple like A, we underfit. If the model's too complex, we overfit, meaning all these complex curves and terms that are used to generate this, it overfits to the training data. And when we get to the testing data, it doesn't it doesn't resemble it whatsoever. Model B is well tuned. It's complex enough to capture the general shape, but it's simple enough to prevent overfitting. It stops us from getting too attached to that test data. The goal in training models is generalization, okay? We're not trying to just fit the best we can or just fit amazingly to one thing and try to make it as good as possible just on very specific data, because that wouldn't necessarily help us. Because let's look at this. Training versus testing, we have a little parabola, or not parabola. We have a little graph that kind of shows, based on model complexity, how much error is there. So on the training data, of course, when we start making it more and more complex, it'll get better and better with less and less error. It'll keep going down as we go towards the most infinitely complex model possible. But now, for the testing data, it's a parabola. Eventually, it starts getting worse on the testing data, because when we make it too complex to the training data, of course, it'll identify the training data perfectly. But will it identify the testing data perfectly is the question. That testing data has a perfect spot right here of complexity that's an optimal tuning point. It's the point where it's specific enough to fit the shape of the data, but it's not so specific that it'll be overfit. It'll be able to be generalized to data of its kind. So there's that perfect sweet spot there. So the whole idea here is, when we're tuning models, we need to make sure to choose proper complexity. It can't be too complex and have too many terms, but it can't be too simple and not have enough terms to represent the data correctly. Now, this is some example kind of code. It's not super important right now, but this is some example code that you can take a look at and try to understand if you know coding. And see, that's how we make actual models here. How to create the models and visualize them, as we did for these demos.